Okay, welcome to the extension of the unit or the semester's review. And one of the things that we're going to have here is that one of the things I pulled up was the parent functions because they wanted you to review that. And what's going to be important for us to review is the fact that at times constant is easy to recognize, so is linear. Absolute value, you have to start knowing that these quadratic U shape, square root, you have no negative numbers. Cubic, it's when you start going from left down, up, cube root, the rational reciprocal inverse function. Actually, sorry, reciprocal inverse rational. This is also known as rational right here. Log looks like this, exponential. Not so much step function, but it's also good to know the sine, cosine, and tangent function. Those other parent functions as well. Okay, great. Let's go ahead and get started. I'm excited to be working on the actual review. So let's go to the review and see. I think I worked on question 6 already. In case I didn't, let me go ahead and write it down. This one is, it's moved 3 units to the right. So this is, oh, you know what, I'm almost sure I did do 6. Let's move on to 7. Let's go to 7, and the directions first ask for us to write out the first 5 terms of the sequence and determine the common ratio or common difference where appropriate. So from here, one of the things we're going to do is this. We're going to discover what the solution is for n equal to 1, 2, 3, and 4. And the results will be this: 4 to the 1, 4 squared, 4 cubed, and 4 to the 4th. So the solutions to that, you just bring out your calculator. I'll be able to do something in my head. 4 squared is 16. 4 cubed should be, I think it's 128, but let's get the benefit of bringing out our calculator and getting an exact solution without any arithmetic errors. Here we go. All right, so now I love the fact that we could just go ahead and do like 4 cubed and discover 64. And then 4 to the 4th, because that's another one I'm going to need, 256. So then I'm able to then prove that this is 64 and 256. So I have the benefit of having the first 4 terms. Now here, one of the other things that they want us to find out, so, first 5 terms. Okay, this is important because that means that this actually should be 5, and this should be 4 to the 5th, which means I need to actually add another value on here. So from here, let's go ahead and discover what 4 to the 5th power is. 4 to the 5th power comes out being 1024. So the solution here is 1024. So there we go. All right, lovely. Now with this one of the things that we have to do, because see, they're asking us for something important, is they're actually asking us to determine if we have an R or a D. One thing that happens, and one of the things that we discover when we look with arithmetic series, this is when you have a geometric series, we have a constant multiply or divide feature in the sequence. And that's actually what is the R value. The R value is the discovery of that constant. When we have a D, this means we have an arithmetic. And one of the things that was important about an arithmetic series is that the A stands for add or subtract. So we could discover a constant add or subtract, then you could guarantee an arithmetic series. So with geometric, the M in there means multiply or divide. Over here with arithmetic, the A stands for add or subtract. So with this one, it's very easy to see that from here to here, this is not a constant difference. You know, it's a difference of 12. Then you describe to see, is there a constant multiply? Now, the way you discover that is you got to take any 2 numbers. One important rule. The actual definition of R is a sub n plus 1 divided by a sub n. So what's important for us to keep in mind that this is really going to be, this being a sequence, so let's suppose that n, you see how we have all these n values over here? Let's just go ahead and we take 1 as an example, because n could be anything here. That means that this is really then R could be a sub 1 plus 1 over a sub 1 which means a sub 2 over a sub 1. And really all this is saying is that this is a sub 1, this is a sub 2. So really what we're doing in essence, and this happens with any of them, you could pick any n, any of these values, and we're going to discover something important, that all it takes is the next value in the sequence divided with the previous. So for example, this is 4. If you want to prove it, take another 2. 64 divided by 16, I'll be able to prove 4. So this guarantees me my r is 4. So if you have 2 of them, then you go ahead and guarantee yourself, like right here, the solution will be r is 4. And that's the constant multiply that's in between them. Okay, now let's do the same thing on this side over here. So let me do a few things so we could make sure we could tell the difference there. And I'm also going to switch colors. And we're going to find the first 5 terms. 1, 2, 3, 4, and 5. Which means we're going to do 6 minus 4 times 1. 6 minus 4 times 2. 6 minus 4 times 3. 6 minus 4 times 4. 6 minus 4 times 5. And the solution comes out being that this is really just 2. This becomes negative 2. This is really negative 12, so negative 6. It comes out being negative 16, so negative 10. And this comes out being negative 15, so, I'm sorry, negative 20, so negative 14. Now, if I go ahead and I want to find, it's to see if there's a difference, actually I do discover it. There is a constant subtract difference. This one there's negative 4, negative 4, and negative 4. And because of that, that's my d value. So this one's a little bit easier to, so d is proven to be a negative 4. So this is my d value, and it's also arithmetic. Now let's go ahead and now use this concept to find the solutions for the rest. Now let me go ahead and I'm going to erase some things to kind of give us the benefit of not having all this work here and just seeing the solution right here for 8 and 9. Now here they want us to find the rule for the pattern of each sequence. So the first thing that's important that we got to keep in mind is this. You're going to kind of have to get a refresh with these rules. These over here give us the benefit of saying everything in the sense of right here. Okay. These rules are all arithmetic. Like if I wanted to find a rule or a pattern, that's what this one does. This gives me the power to find, to find the rule. And the rule also gives you the power to find a specific term or like some kind of end value. This is summation. This is for infinite sums. And this is only for geometric. See how there's R? So this one does fall into a little bit into geometric. This is right here, but these are for arithmetic is for these two. Now geometric is over here. And this is the same thing. Rule or term. Sometimes we need both. And this is for the summation of it. It's a quick way to add. And then we have also the geometric here as far as expansion. All right, lovely. Let's go ahead and go back and kind of look at these concepts. Now here they want us to find the rule or pattern. First thing we have to do is determine it's geometric or arithmetic. Now with here, when I look, I discover 6, 6, and 6, and 6. So that guarantees me that it's arithmetic, first of all. And the other thing is that d is 6. So with that, I'm going to just use this equation. A sub n is equal to a sub 1 plus n minus 1 times z. So with that, I have the power then to move this for a second and go ahead and fill in the rest. A sub n then is going to be, this is a sub 1. It's the first term in the sequence. It's going to be 3. Hold on, let me take away the comma. I don't need it there. What I do need is the solution to the rest. N, we're going to leave it like that. That's how you determine room. This is going to be 6. So what you do is you distribute, and then this becomes n3 plus 6n minus 6. And your final solution comes out being 3. I'm sorry, not 3, because that's going to combine. The thing I love is that we discover a simplification, so we get that this is really 6n. Let's go ahead and again make that the correct letter. 6n minus 3. So that's the solution. And anytime you want to prove it to yourself, go ahead and put in some numbers. Like if I put in 1 in there, I do get 3. If I get 2, I do get 9. So you can always prove if you have the correct rule or pattern by just plugging in some few numbers. Okay, let's go ahead and look at B. Now from B, one of the things I discovered that this is 8. The difference between here is then 24. So automatically, no longer it's no longer arithmetic. Now, so let's go ahead and discover to see if it's geometric by chance. So the way I do that is I take two numbers and divide them. Again, remember one preceding the other. And one of the things we get is that this 3. And then I take another 2 and divide them. I get the same 3. So that guarantees me that it is geometric. And that the R is equal to 3. So with that, we're going to use slightly a different equation. We're going to be using this one. One of the things with geometrics is we discover that a sub 1, r, n minus 1. So simply put, a sub 1 is still this first term. So we'll have 4, we'll have 3, and then we'll have n minus 1. Again, if you want to prove you have the right solution, just go ahead and type it in, or go ahead and work out a few. 4, 3, 1 minus 1, 4 times 3 to the 0, 4, because this is really 4 times 1. All right, and if you move on to 2, this means that this is really 1. Solution comes out being 12, because it's now 3 to the 1 power is 4 times 3, and then the means of the second. With that, you're able to prove that, at least if you get 2, then you're able to prove that you did do it right. All right, lovely. Let's go ahead and move on to the next one. Same thing, we're going to erase, just make some space. And make things a little bit nicer here. All right, lovely. It says now, here it says evaluate the sum. Now, the expansion of this, one of the things that we got to keep in mind with this, this is the start. This means adding. This means this is a symbol for Greek to add. So that's exactly what, when you see a summation, it was a convenient way to tell you a lot of things that are necessary. Because see, these sequences, they could go on forever. See these little 3 little dots? That means it keeps on going forever. Sometimes it's not so necessary to get everything added up. Sometimes we just need parts, chunks. But when we're dealing with some things that in our world are finite, it's important to know where to start, where to end, and what the equation is. So simply put, this is saying that I'm going to go ahead and add values 1, 2, 3, 4, 5, and 6. So that means that this expanded looks like this. 4 times 1 minus 2 plus 4 times 2 minus 2 plus 4 times 3 minus 2. Oops, no parentheses there. It's more of a plus 4 times 4 minus 2 plus 4 times 5 minus 2 plus 4 times 6 minus 2. Okay, and then when you add them all up, that'll be your solution. So, you know, I'll be able to do this kind of quickly for you. I'm going to do it in red, though, so we can find the difference here. This is going to be 2 plus 6 plus, it's probably going to be 4, which would be 10, 14, 18, and 22. So that means from here, just bring out your calculator and just add those together. 2 plus 6 plus 10 plus, oh, well, I missed a bunch of things here. 2 plus 6 plus 10 plus 14 plus 18 plus 22, 72. So the solution, actually, the summation of this is 72. All right, lovely. Okay, now they want us to, let's go to 10. They want us to express the sum using summation notation. Now for this, we're going to have to do everything backwards. That means that it's important to define the start, define the end. So we're going to define the start, the end. We know we're going to add it because they're asking us to express already in that kind of format. And we also need to come up with the equation. So let's discover, first of all, what the equation is. Now, if I look at this, this one actually has a couple of mechanics into it. First of all, I'm going from 2 to 4 to 6. So it is, it's actually just 2 times n, because I'm going to 2 to 4 to 6. So if I was looking at that, yeah, I have an r is 2. Let's see. Let's see if this is if this is 4 to 2. Okay. Now, one of the things with this one, if I look, this sequence is constantly adding by 2. So like this is going 2, 2, 2, 2. So this is the d. Like if you wanted to find out using an equation, this d is 2, because you can see how that's 2. And so the equation would just go like this: a sub n is equal to 2 plus n minus 1 times 2. And one of the things that we discover that this is really 2n minus 2. These negative 2's cancel, so it's really just 2n. And that's actually what I was going to write down, just 2n, because I was able to describe that in my head. And then you do the same thing here. Actually, when you look at these little power signs, I kind of covered that one up. Let me highlight them better put. When I look at the little highlighted ones, there. Oh, those things are huge. The benefit that I get is that they're also going in an arithmetic fashion. So if you want to use an equation to discover what that is, it would actually be the same thing. No, it wouldn't be the same thing, because d is 1 in this case. So to really find out what that is, you will have this. Let me erase this over here and kind of share with you what we're going to be working with. First of all, we discovered that d in that equation, like between here to here, and then in the power part is going by a difference of 1. A sub 1 is actually 2. So when you write it in the equation, a sub 1, it will be 2 minus n minus 1 times 1. So when I distribute this, I'll get, let's see, 2 minus n. Oh, I'm sorry, that should be a plus. That shouldn't be a minus. That should be 2n minus minus 1. So then this is really just n plus 1. So which means that this little part that's up here, this power, this equation is really described as n plus 1. Now, talk about the start and the finish. Okay, this is kind of important here, because one of the things that we're going to do is that we're going to start our start now almost always. And in this case, in elementary number theory, like we're working with, we're going to go ahead and put the start point in 1, and it's almost as a given. So just expect that that's going to be with everything we do. Now the end is actually going to come up from here. Now you see how the last term is 9? That means, like, if you expanded this, since we know that this is 1, and you kind of started 1 ahead, that means there's actually only 8 terms in here. And if you want to prove it, you could actually write them out. Like if you want to put 2 squared, 4 cubed, 6 to the 4th. The next one will be 8 to the 5th. Next one will be 9 to the 6th. Next one will be 10 to the 7th. Oh man, how many I have? Already 11 to the, no, not 11. I kind of went out of sequence here. Let's fix this. This should be 10, 12, 14, 14 to the 8th, 16 to the 9th. But when I count them, 1, 2, 3, or a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, a sub 7, a sub 8. And that's how you know that there's actual 8 terms in here. Starting with that one and going all the way to 8. Okay, great. Let's go ahead and move forward to the next part, which here's find the sum of the infinite geometric series. Okay, for this one, there was a very special, easy, simple equation that we use. When you look at your formula chart, it's this one right here. Let me see if I could write on here so I could. It's this one. And really what it meant is this. If you discovered that r is less than 1, like if r is a fraction, then pretty simply put, the solution to this would just be written a sub 1 and 1 minus r. So let's go ahead and discover what r is. The difference between the there, so negative 12 over 24. Let me fix that. Negative 12, 24 is negative 1/2. Now when I do a second one to prove it, negative 1/2. This is important because that means that this is a fraction. Where my fraction needs to be less than 1. Absolute value sign. And it is in this case. So once I determine that, then a sub 1, this is 24. And it's pretty easy as far as the use of this equation. Minus negative 1/2. This simplifies to the solution of 1 plus 1/2. And I want to combine these two as a fractions to simplify. So if I do 2 over 2, this becomes 24 over 3/2. And then from there, we just use our simplification some more. 2/3, 48. It's really a fraction. For those who are wondering how I got 48, 24 times 2. And 1 times 3, 3. So I'll be able to guarantee that this thing is going to actually converge and add up to 16 as we go to an infinite. That's how you know that this is different. Why that word? Now here it says 12. It says find the fifth term and the rule of the geometric sequence for the initial term t1 common ratio given. Oh, this would be pretty simple. Really what they're looking for is this. Okay, say a sub n. They're looking for a sub 5. So I'll write it first as a sub n, so you'll see what's going on. Remember the equation. Let me write it one more time because I know some of you probably haven't yet have it all memorized. A sub 1 r n minus 1. So actually, let me fill everything in at once. I know that the fifth term, so this is 5. I was given a sub 1, the same thing as t sub 1. 4, 5 minus 1. So a sub 5 is guaranteed to be 3 to the 4 to the 4th power there. So simply put is, let's go ahead and quickly solve this. 4 to the 4th. Ooh, not that one. 4. 768 will be the solution to this. So 768. Lovely. Let's go ahead and move on to the next one. Okay, it says find the indicated coefficient or expansion. There is a formula for this. Let me show you which one it is. If we go back to here, this has to do with binomial theorem. And one of the things that we had the benefit of doing is that if we were looking for a specific term, you just had to use that, which was n j minus 1, n minus j minus 1, and b j minus 1. Let's go back here. It was going to be n j minus 1, a. Let's go back and just take a look real quick. N minus j minus 1. So let's see. Let's go back over here. N minus j minus 1. And it was b. I think it was just j minus 1. But just let me just verify. Yeah, it's j minus 1. Okay. Now, if you notice, there's a lot of j minus 1s here. And that's because, first of all, this is written in this format. This is a plus b n. So it tells me that a is 3x, b is 2, minus 5. So I got 5 things that I need, 3 things that I need right off the bat from this equation. This is the j. So actually, since there's a lot of j's here, j minus 1s, it's probably easiest just to take this j, which is 5, and subtract 1. So it's 4. So I now could simplify this a lot. I go ahead and write this as 5, choose 4, a minus 5 minus 4, b to the 4th. Oh, and I know exactly what a and b is because I already solved that for as well. This is 3x, and over here this is 2. Okay, so let's go ahead and solve this. Now, one thing that's probably the newest part about here is that 5 choose 4. There's a special command. What you do is you put in 5. You go to math. You go over here to this probability screen. And what you're going to be looking at is actually this part right here. See where it says n choose r? That's exactly what you want. So we're going to go ahead. We're going to go ahead and choose that option. We're going to choose 3, choose 4. And one of the things, you could do it by hand. I think there might be the formula there. But this is the easiest method. See how it says 5? So that means it guarantees me this will be 5. This is then going to be times 3x to the first power, and then 2 to the 4th. So we got 2 raised to the power of 4. So it'd be 16. Now the only thing that this problem I think kind of robs of the whole situation, and then you multiply the numbers. So it would be 5 times 3 times 16. I do want to give you a word of caution. So the solution here is 240 times x. This is the actual solution to the 5th term of this expansion sequence. There's a word of caution I do want to share with you. And the word of caution is this. That this one did not, well, if I was going to do this, this is a power. But technically you're supposed to change to each of those. So this really would have been simplified 3 to the 1, x to the 1. Now we know that these 1s actually reproduce the same thing, so it didn't have any effect. But if this was a square, like if this was a different number altogether, then it would have an effect. So that's the word of caution I want to bring out. In case if you experienced that during the final exam, then you can go ahead and actually use it. Okay, now this one they want us to expand using the binomial theorem. The easiest thing that you could do in understanding this, we did Pascal's triangle. You could do a lot of review into that and everything else. But simply put, the mechanics work like this. You had that this was n, 0. Well, you started 0. You started at the lowest value, basically. And then afterwards you went a to the n, b to the 0. I wonder how they have it written actually on the formula chart. Yeah, no. It's written like this, n minus j. And the j is the term you're going to. J is being 0. So it is like that, where those j's are 0. But the thing that's important about this is a couple of things. First of all, this is going to go down in value in each step. This is going to go up, down, and up. So follow me on this. First of all, let's go ahead and write down a. A is 5x, b is 3, and n is 3. Okay, so taking this, and I could go ahead and rewrite it as 3 to 0 plus, well, not plus. And my recommendation is this. You want to start, actually the way they have you start is they have you write parentheses, and then you take the a value, which is going to be 5x, rise to the highest power. So like in this case, 3. Take the b value, which is going to be 3, right to the 0 power. And afterwards, you write another parentheses, and then you start going down the value. Like this is going to go down. This is going to go up. So you move the next term, but square. See how it went down 1 value? And this next one will go up 1 value. And you keep on doing that. So like... kind of making myself run a little bit out of space here. Look here, this comes out being 5x to the first, 3 squared. And the last value comes out being 5x to the 0 power. And these are actually all in parentheses. This is important because the way they distribute, and I do want to go over that. 5 to the 0, and then this is times 3 to the 3rd power. So then afterwards you put these n choose r's. And this is where you can do Pascal's triangle and kind of do a shortcut into it. But this will start at 3, 0, 3, 1, 3, 2, 3, 3. So you see they go up in value this way. And then from there it becomes a little bit more manageable to actually do. One word of caution. Now if I did Pascal's triangle, it makes it easier. 1, 2, 1. I'm going to do it to the 3rd level. Remember we add these. Let's see. Forgot those ones there. 4, 6. Actually, this will be the level. I really don't need to continue further than that. So that means that this is really 1. And you could do the n choose r with your calculators and discover that these are the solutions. 3, 3, 1. Afterwards, this is what we do. You distribute this 3. So this is what's going to happen. The first term is going to be then just 1 times 5 to the 3rd x cubed. And then 3 to the 0 is just 1. Second term, let me move that over here. The second term is going to be 3. Remember, distribute. 5 squared x squared times 3 plus the next term, which would be 3. Distribute, well, you could distribute the 1, but it's really just 5x times 3 squared plus, let's see, 1 times 1. 5 to the x raised to the power of 0 just becomes 1. And then 3 squared comes out being 27. Yeah. So if you want, you could just write that solution there. All right, so let's go ahead and simplify this. 5 cubed should be 125 x cubed plus, this is really 25 times 9. Because remember, this is really 25. And I have 3 times 3 here. So it'll be 25 times 3 is 75. And then you multiply by another 3. 225. So 225 x to the squared. And then this becomes 3 times 5 times 3 squared. So 3 times 5 times 3 squared. So which comes out being 135 x. And then lastly, this thing's 1 times 1 times 27. So the solution comes out being 27. So here's your solution for that one. All right, good. Let's go ahead and now move into polynomials. This was the last of the binomial theorem. Now with polynomials, we discovered a few things, a few properties as well on these. So let's go ahead and go over them. One of the things that we discovered was the fact that this form a polynomial whose zeros are given. Anytime you're given a 0, like for example this, in order to guarantee that it's going to cross a -3, you have to do the opposite of what's there. For example, let me bring up Desmos to kind of show you how that is in works. Let me go up here, go to Desmos. Okay. So if I wanted to cross a -3, one of the things that you discover, there, you have to do the opposite of what it shows, x plus 3. Okay. Now, one of the items too with here, so like with this one, says multiplicity of x, so x plus 3 will make that polynomial. You see how it says multiplicity of 3? That means that the power is 3 there. Now, one of the things that happens is that they turn depending on the multiplicity. For example, let's go back here. One of the things I get, if it's odd, you're guaranteed to turn. So let me go over here and cube. Actually, no, I'm sorry, the other way around. If it's odd, you're guaranteed it's going to cross. And actually, if it's greater than 1, you're guaranteed an inflection point like this. So that's how I discovered that. Let me go back over here and then move on to the next one. This one's multiplicity of 1. So in order to have, just did something that that. Bring it back to the way, well, I'm not exactly sure how it was, but let's just keep on working onto this. So then the next one is multiply, but it's going to be x minus 1. Remember, it's going to be opposite, which you see multiplicity is at 2. You see the 4 at the end? This means that's x, not plus. We're going to have to do minus to describe that crossing that 4. Minus 4, and there you go. Now, the way you guarantee that it is a degree 6, this last part, is that these all add up. Basically 3 plus 2 plus 1. 3 plus 2 plus 1 is guaranteed to be 6. So that's how you get that's the degree. So when it asks to identify, and this is important because the power function, something like a parent function, is just a quick way to tell the end behavior. Now this is 1, that's 2, that's 4. So that's how you discover what the power function is. Like in this case, take x and you add 1, 2, and 4. And the power function then is guaranteed to be then 7. So this polynomial is going to have a lot of the same end behavior as x to the 7. Now this one here, let's move on. 17 says use the factor theorem to determine whether x and c is a factor. All right, so what you're going to do is you're going to do synthetic division. Now if you're given the c value already, you do not need to modify. You don't need to change it. And with this, remember, you got to put in any missing powers. This is missing a 0x squared there. So when I write this, write the coefficients 4, 10, 0, 15, negative 9. And what's important to keep in mind that this is going to be my add row, multiply row. So anything that falls in there, so like if this is 4, I'm going to multiply with the c value, so negative 3 times 4 is negative 12, and then this is the add row, so it's negative 2, negative 3 times negative 2 is negative 6, I add it together, negative 6, negative 3 times negative 3 times negative 6, that is positive 18, so we come out getting a solution of 32, no, 33. And the last one is going to be negative 99. So this solution goes out being negative 108. Is the last part. So this one has a remainder. It's not a factor, but they want you to still use, so it's not a factor. They still want you to write it in this form. So if that's true, then we're going to do this. It's x plus 3. And then it's, remember, you always start one less power because technically what we did is we divided. So this is 4x to the cube plus negative 2x squared plus negative 6x plus 33 plus negative 108 divided by this x plus 3. That's how you write it in factor term. Now this one, they want us to list all possible zeros. This is when we do the whole thing to do with p's and q's. So remember, this is q, this is p. List the factors. So for example, the here for 12, just list down that we know that's 1 and 12, 2 and 6, 3 and 4. That's it. For 3, the benefit of seeing that's just 1 and 3. So if that's the case, then all we have to do then is p divided by q. So like in this case, it's going to be, oh, and then you write each one. Before we do p divided by q, take your p's and put everything plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And the q's, we did the same thing. Actually, probably be a good idea to move this up just a little bit so I can have rooms for the q's. And it becomes easy to kind of see the division of them. I'm probably going to change the color for the q's so we won't get confused. Plus or minus 1, plus or minus 3. So we're going to divide them all. And first of all, 1 is going to divide into all of these. So we're going to have a repetition of a list. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And then 3 is going to divide all these. So plus or minus 1/3, plus or minus 2/3, plus or minus, well, I don't repeat that one, but I go to 4/3. I don't repeat the next one or the next one, so that's it. We stop there. The reason I didn't list any other ones because they're repetitions. It'd be like 1, 2. There'd be things that I already have listed, so you don't list repetitions. Okay, let me go ahead and end it for here, and then I'll continue for the next one on the rest.